I look into Antarctic sea ice and its role in fertilizing the Southern Ocean. So we're basically looking at microscopic marine plants in the oceans. They remove carbon dioxide from the atmosphere by photosynthesis, and they therefore play a key role in regulating the Earth climate. Now, in the Southern Ocean, those small plants have plenty of water and they have light, and they also have micronutrients, but they're limiting by one element, which is iron. Iron is basically the nutrient that phytoplankton needs, and phytoplankton is at the base of the food chain. So not only that phytoplankton can take up carbon dioxide from the atmosphere, but it's also serve as critical food for Antarctic krill and then higher trophic levels like seals and birds and whales. So if we can try to understand how the functioning of that iron delivery can impact on phytoplankton, then we can understand how much carbon dioxide can be taken up, but we can also understand what's the outcome for higher trophic levels and also fisheries. When we look at sea ice is like frozen water around Antarctica. That sea ice contains really high amount of iron as well as algae. And when it melts every year, that ice releases iron and organic matter and those small phytoplankton into the water column, and then you get massive algal blooms every year, and you can see them from space. What I try to see is whether the predicted reduction in the sea ice thickness and extent will actually change the mode and the magnitude of that delivery of iron to Antarctic surface waters. The more iron you will have, the more productivity you will have, and eventually the more carbon dioxide from the atmosphere you will take up. The best way to actually do our work is to do as much as we can out at sea. And we use the sea ice as a big open air clean rooms. It's the most pristine air you can have. So we use that to our advantage because we're looking at very low level of ions and we don't want to contaminate them. So we try to do as much as we can out there. So we cut the ice out there and then we melt it back on board and we filter it. And then those samples are kept frozen until we get back to Hobart, and the rest of the processing is done at the university here. I did my PhD in Belgium and then came here down to Antarctica. Actually, I went on board the Australis in 2003, and I thought I'd come back to do research here at UTAS, and here I am. This project and this research is highly multidisciplinary. You can't just be a chemist. You have to know a bit about biology, about analytical chemistry, about glaciology. And here at UTAS we have all those ranges of research all put together. So during my research I work a lot with analytical chemists here at the CSL. I work with glaciologists here at the ACRC. I work with biologists and ecologists at the Antarctic Division. So it's a very good environment to flourish and learn a lot from other disciplines.